Right now, as you lie there, the night sky above you looks perfectly calm. Steady points of light, patient and unchanging, the same quiet stars that humans have always fallen asleep beneath. But that calm is a report on your own eyes, not on the universe. Because out there, past the edge of what you can see, a star is surviving its own death. Our galaxy is quietly eating another one. A black hole that gives off no light is crossing the dark between the suns. A magnetar the size of a single city is straining toward the fracture that will fling its fury across the galaxy. And something we cannot see is pulling our entire galaxy toward it at 14 million miles per hour. None of it makes a sound. None of it asks our permission. The most terrifying things in space were never the ones you could see coming. Get comfortable. Hit subscribe if you're new here. Because by the end of this, the calm sky above you is going to feel very different, and you will understand just how much it has quietly been keeping from you. Now let's slowly ease into this. Part 1. Number 10. The Stars That Refuse to Die. Let us begin gently, with something that should not be frightening at all, and then let us sit with it until the fear arrives on its own. A star is born, a star lives, and a star dies. That is the whole story, and for most of the history of astronomy it was told with the confidence of a law. The largest stars burn through their fuel in a few million years and end in a single catastrophic explosion. The smallest ones smoulder for longer than the present age of the universe, and a star like our own sun sits somewhere in between, destined to swell, to shed its outer layers, and to leave behind a small, dense, cooling ember called a white dwarf. Death, in this account, is the end. The explosion happens, the star is gone, and the books are closed. What I want you to notice tonight, over and over, is how often the calm night sky is not a description of the universe at all, but a report on the limits of our own eyes. And nowhere is that clearer than here, at the very edge of stellar death, where astronomers found something that has no business existing. They found stars that survived their own deaths. To feel why that is unsettling, you have to understand what kind of death we are talking about. There is a particular sort of stellar explosion called a Type 1a supernova, and for a long time it was treated as one of the most reliable events in all of nature. The recipe is simple to state. Take a white dwarf, that dense ember left behind when a star like the Sun finishes burning. Give it a companion star close enough to steal matter from. The white dwarf pulls gas onto itself, growing heavier and heavier until it reaches a critical threshold, a tipping point in mass beyond which it can no longer hold itself up. At that moment, a runaway wave of nuclear fusion tears through the entire star in a matter of seconds, and the white dwarf is utterly obliterated. Nothing is supposed to be left. The explosion is so consistent, so predictable in its brightness, that astronomers use these events as measuring sticks to gauge distances across billions of light years. They are the yardsticks of the cosmos precisely because they were thought to be total, complete destruction, every time. And then, beginning around the year 2013 and confirmed with careful work in the years that followed, astronomers found a class of these explosions that broke the recipe. They called them Type 1ax supernovae, and the informal name that attached to them tells you everything about how strange they are. Zombie stars. Because when astronomers went back and looked closely at where one of these explosions had occurred, they found that the star was not entirely gone. Part of it had survived. The supernova had detonated, released an outpouring of energy, blazed across intergalactic distances, and yet, when the light faded, a wounded, transformed, still-bound remnant remained where the star had been. Something had walked out of its own funeral. The clearest case came from a supernova catalogued as 2012Z, which flared in a galaxy known as NGC 1309. When astronomers pointed the Hubble Space Telescope back at that exact location and compared images taken before and after the blast, they found evidence of a surviving system, a bound remnant lingering at the scene of what should have been complete annihilation. This was not supposed to be possible. A star had undergone a thermonuclear explosion powerful enough to be seen from another galaxy, and a piece of it had refused to be destroyed. Imagine setting off the most violent event a star can experience, an explosion that for a few weeks can rival the light of 100 billion ordinary stars, and then looking at the ashes and finding a heartbeat still there. I want you to stay in that image for a moment, because it is worth dwelling on. Picture the surface of a white dwarf in the instant the runaway fusion begins. The star is roughly the size of the Earth but carries the mass of the Sun, so its surface gravity is crushing beyond anything in human experience. Now the fusion ignites, but not evenly. Instead of a clean, symmetric detonation that consumes everything at once, the burning begins on one side or in one region and rips outward unevenly. A wall of nuclear fire tears off one flank of the star and hurls it into space at thousands of kilometers per second, a blinding, lopsided eruption. And at the core of that light, where the burning never fully caught, a scarred core holds together. It is battered. It is reshaped. It is thrown across space by the recoil of its own explosion, a survivor kicked out of its former life at tremendous speed. But it is still, in every meaningful sense, a star. It endured the one event that was supposed to be its ending. The leading explanation for why this happens is exactly that asymmetry, that incompleteness. In an ordinary Type 1a event, the fusion consumes the whole white dwarf. But in these partial explosions, something about the ignition or the star's structure lets the burning fail to finish the job. The detonation becomes a deflagration, a slower, weaker, more uneven burn that blows off a great deal of material but leaves a remnant intact. And here is the part that turns a curiosity into something genuinely disquieting. These events are not vanishingly rare. Astronomers now suspect that a substantial fraction of what they once catalogued as ordinary, total supernova, perhaps up to a third of the events in that broad family, may actually be these partial explosions with a survivor left behind. Which means that one of the processes we treated as the most final, most reliable form of stellar death might frequently not be an ending at all. Consider what that does to the neat story we started with. We said a star is born, lives, and dies, and that death is the end. But if a star can pass through the fire of its own supernova and come out the other side still bound, still shining in its damaged way, then even death, the most absolute thing we thought we knew about, is not guaranteed. The universe has found a loophole in one of its own most fundamental processes, and that is the first thread I want you to carry with you through everything that follows tonight, because it will keep returning in new forms. The things that frighten us most in space are rarely loud monsters lunging out of the dark. They are quiet violations of rules we assumed were unbreakable, a rule as basic as this one dies, and it stays dead. Except, apparently, when it does not. There is a personal edge to this one too, and it is worth naming softly, because it brings the cosmic down to something you can feel. Our own sun is destined to become a white dwarf. In roughly 5 billion years it will exhaust its fuel, swell into a red giant, shed its outer layers into a glowing shell, and leave behind that same small, dense ember that sits at the centre of this whole story. Now, our sun is very likely alone in the relevant sense. It does not have a close stellar companion to feed it, to push it over that critical threshold, and so it is not expected to end in one of these explosions at all. It should simply cool, slowly, over an almost unimaginable stretch of time, into a cold, dark cinder. But the category is real. The kind of object our sun will become is precisely the kind of object that can, under the wrong circumstances, detonate, and then partly survive its own detonation. The ember at the end of our star's life belongs to the same family as the cosmic revenants we have been describing, and notice what these survivors are physically. They are not ghosts and they are not metaphors. They are real objects, scarred and reshaped, moving through their galaxies at high speed, carrying in their very structure the record of an explosion that should have erased them. If you could somehow examine one closely, you would be looking at matter that has passed through a nuclear firestorm and held together, an object whose entire existence is a contradiction of what stellar physics predicted. There is something almost unbearably strange about that. We tend to think of the universe as a place of firm rules, where energy on that scale means total destruction. And here is a class of objects whose only real crime is to keep existing after the rules said they should not. This is why I called the calm night sky a report on our eyes rather than on the universe. When you look up, you see steady points of light, and it is easy to imagine them as simple, orderly things, each one obediently following the life and death script we wrote for it. But hidden in that catalogue of quiet lights are stars that broke the script. Objects that experienced the most extreme event in a star's existence and did not have the decency to disappear. We only found them because our instruments finally became sensitive enough to go back and check the ashes, and to notice that something in the ashes was still there. Before that, we simply assumed the deaths were total, because that is what the tidy story required, and because we could not yet see well enough to know otherwise. There is a practical wrinkle here that makes the discovery even more interesting, and it is worth a moment of your attention because it shows how one strange object can quietly unsettle a whole field. Remember that ordinary Type 1a supernovae were treated as reliable measuring sticks, standard candles, objects of such consistent brightness that astronomers used them to gauge distances across the universe and even to discover that the expansion of the cosmos is speeding up. That entire method rests on the assumption that these explosions are uniform, that they all work the same way. But if a meaningful fraction of what we lumped into that category are actually these partial, incomplete zombie-making events with a different mechanism and a different brightness, then some of our most important cosmic measurements were quietly contaminated by objects that do not follow the rule. Astronomers have worked hard to tell the two kinds apart, and they largely can now, but the very existence of the imposters is a reminder of how a single broken assumption can ripple outward into places you never expected it to reach. And what becomes of the survivors themselves, these stars that walked out of their own funerals? This is where the story turns almost mournful. A zombie star is not restored to health. It does not simply resume its old life. It has been fundamentally changed by what happened to it. Much of its outer material has been blasted away. Its structure has been reordered by the partial burning, and crucially it has been kicked. The lopsided explosion that failed to destroy it also shoved it, hard, so that these surviving remnants are often flung across their galaxies at high speed, runaway stars carrying the scars of the fire they endured, no longer part of whatever quiet binary system they were born into. If you could follow one, you would be watching a wounded thing racing away from the site of its own near annihilation, forever marked, forever moving, a refugee from a death it should not have survived. There is something almost unbearably lonely in that image, and it is a loneliness we will return to again tonight, in larger and larger forms. So we have our first entry, and already the ground feels slightly less solid than it did a few minutes ago. A star can survive its own death. That is unsettling, but it is also, in its way, small and contained. It is one strange class of objects doing one strange thing at the scale of individual stars. The fear here is intimate, almost quiet. But the universe does not stay at this scale. The next thing on our list is not one strange star, but an entire galaxy. Our galaxy, the one you live in, the one that made every atom in your body. And what I have to tell you about it is that it is not the peaceful permanent home you were raised to picture wheeling slowly overhead. It is doing something right now, tonight, as you listen, that we do not usually let ourselves think about. It is feeding. Part 2, Number 9, The Galaxy That Eats. We like to think of our galaxy as home, and home is supposed to be a safe word. The Milky Way, that soft band of light arching across a truly dark sky, feels like the most stable and gentle thing imaginable, a great slow wheel of stars turning once every couple of 100 million years, patient and eternal and kind. It is the setting of every night sky you have ever loved, and I have to tell you as gently as I can that this setting has a secret, and the secret is that our galaxy is a predator. It grows by hunting. It has spent billions of years catching smaller galaxies that drifted too close and tearing them apart and absorbing their stars, and it is doing exactly that right now, tonight, to a galaxy that never had a chance. The victim currently being consumed has a name. It is called the Sagittarius Dwarf Spheroidal Galaxy, and it is a small companion galaxy that wandered into the Milky Way's gravitational reach and is being pulled to pieces. Not in a sudden violent event, but in the slow, patient, almost tender way that overwhelming gravity does its work. The Milky Way's tides stretch the little galaxy, drawing long streamers of its stars out in front of it and behind it, unwinding it like thread pulled from a spool. Over hundreds of millions of years the small galaxy loses cohesion, its stars scattered and mixed into the greater whole, until eventually there is nothing left of it as a distinct thing at all. Its stars become our stars, its identity is erased, and from the point of view of anyone who might once have lived there, the sky that had been their home galaxy is simply dissolving into something larger and indifferent. This is not a one-time event, and it is not ancient history that happened once and stopped. It is the ongoing method by which our galaxy has always grown, and the evidence is written across the sky in a way that, once you know how to read it, is genuinely haunting. Threaded through and around the Milky Way are long, faint ribbons of stars called stellar streams. There is one known as the Helmi stream, and another called the Virgo stellar stream, and others besides. Each of these ribbons is the digested remains of a galaxy that our own galaxy consumed in the distant past. They are the trails left behind by meals. When astronomers map these streams, they are quite literally reading the record of ancient predation. The tidal debris of smaller galaxies that existed once had their own histories and were swallowed whole hundreds of millions or billions of years ago. And here is a detail that makes it stranger still. Astronomers can point to individual stars in our own galactic neighbourhood and say, with real confidence, that these particular stars were not born here. They can tell because the stars carry a different chemical signature, a different mixture of elements from the ones that formed in the Milky Way, and they move along different orbits, marching to the rhythm of a galaxy that no longer exists. These stars are immigrants, in the most literal possible sense. They are refugees from consumed worlds, still moving through space in the patterns their vanished home galaxy set for them long ago, now surrounded by the stars of the predator that ate their birthplace. Some of the light you see when you look up at certain patches of sky is coming from stars that are in effect evidence of a crime, and the manner of it, if I can put it this way, is part of what makes it so unsettling. When we say the Milky Way tears a galaxy apart, it is easy to picture something sudden and loud, a collision, a crash. But that is not what is happening at all. Gravity does its work slowly and without violence in any way we would recognize. The little galaxy is not smashed. It is stretched. Over hundreds of millions of years, its stars gently coaxed out of their orbits one by one, drawn into long, graceful arcs that unwind across the sky. From inside the doomed galaxy, if there were anyone to watch, nothing dramatic would ever seem to happen. Generation after generation would look up at a sky that appeared perfectly stable, and only across spans of time no living thing could perceive would the shape of everything slowly, silently come undone. That is the signature of nearly everything on this list, and it is worth naming plainly now, because it will return again and again. The most frightening processes in the universe are almost never loud. They are patient. They unfold on timescales so far beyond a human life that from the inside they look exactly like peace. The Milky Way is committing an act of consumption so slow that every human who has ever lived has looked up and seen only stillness and called it the eternal, unchanging heavens. I want to slow down here and let the human weight of this settle, because it is easy to keep it abstract. Think about what it would mean for a galaxy to have been consumed. A galaxy is not a small thing. Even a modest dwarf galaxy can contain hundreds of millions or billions of stars, and around some fraction of those stars there may once have been planets, and on some tiny fraction of those planets, over the enormous stretches of time involved, there could have been life, and perhaps even minds that looked up at their own night sky and felt at home. If any such civilization ever arose in one of the galaxies our Milky Way has eaten, then the physical remnants of everything they ever were, the atoms of their worlds, the scattered light of their stars, are now drifting silently through our own galactic neighbourhood, mixed in among us, unremarked and unrecognized. Calculations suggest that stars torn from the Sagittarius dwarf could pass within tens of thousands of light-years of our own solar system. The digested remains of another galaxy are not far away in some abstract cosmic sense. On the scale of the Milky Way, they are practically next door. This is the second thread I want you to hold, and it connects directly to the first. With the zombie stars, we saw that even stellar death is not always final. Here, we see that even the sense of home, of belonging to a stable and permanent place, is an illusion built on a slower timescale than a human life can perceive. Our galaxy is not a fixed and finished thing. It is a work in progress, assembled over billions of years out of the shredded bodies of smaller galaxies, and it is still assembling. The soft, eternal-seeming wheel of the Milky Way is a predator caught in the middle of a meal so slow that from inside it, over the span of all recorded human history, nothing appears to move at all. And that is exactly the point I keep returning to. The calm is a report on the shortness of our lives, not on the nature of the thing we are watching. And the Milky Way's appetite is not satisfied. It is not going to stop with the small galaxies it is currently digesting. Far out in the dark, at a distance of about 2.5 million light-years, There is another great spiral galaxy called Andromeda, larger than our own, and it is falling toward us, or we are falling toward it. The two are being drawn together by gravity, and in roughly 4 to 4.5 billion years, they will collide. This is not a metaphor or a maybe. It is one of the most confidently predicted events in all of astronomy. The two galaxies will pass through each other, be pulled back, pass through again, and over a chaotic stretch of hundreds of millions of years, they will merge into a single immense elliptical galaxy that astronomers sometimes playfully call Milky Way. Now, I want to be careful and honest here, because the picture your imagination probably just painted is not quite right, and the truth is stranger. When two galaxies collide, the stars themselves almost never actually strike one another. Galaxies are overwhelmingly empty space. The distances between stars are so great compared to the sizes of the stars that two entire galaxies can pass straight through each other, and hardly any stars will collide at all. What happens instead is that the gravitational choreography is completely rewritten. Star systems are flung out into the space between galaxies, cast into a lonely intergalactic exile. Others are dragged into new orbits. Great tides pull long streamers of stars across hundreds of thousands of light years, exactly like the stellar streams we already talked about, but on a far grander scale. Our own solar system could well be thrown outward, relocated to some distant fringe of the merged galaxy, or hurled entirely into the dark between galaxies, and at the very centre, the supermassive black holes that anchor each galaxy will spiral toward one another and eventually merge in an event that will shake the fabric of space itself. There is something quietly disturbing about the erasure this represents. When the Milky Way and Andromeda finish merging, neither of the two beautiful spirals will still exist. The particular arrangement of stars that we call the Milky Way, the shape that has hung over every sunset and every night of human history, over every civilization and every story ever told beneath it, will be gone, blended into a featureless elliptical blob that bears no resemblance to the galaxy we called home. Everything cosmic that we think of as our permanent backdrop is, on a long enough timescale, temporary. And the atoms that make up your body, forged in ancient stars and scattered by ancient explosions, will very likely end up as part of a galaxy that would be unrecognizable to anyone alive today. I want to add one more layer to this, because it changes how you understand the very body you're sitting in. The Milky Way did not arrive in the universe fully formed. It was assembled over more than 10 billion years out of smaller pieces, out of countless dwarf galaxies and streams of gas and clusters of stars that fell together and merged and were absorbed. When astronomers study the oldest stars in our galaxy, the ones in the great spherical halo that surrounds the bright disk, they find a population of ancient immigrants, stars that formed in other smaller galaxies long ago and were folded into ours during those early feasts. Our galaxy is, in a real and physical sense, a collage of its victims. The spiral you picture when you think of the Milky Way is not a single thing that grew in isolation. It is a composite stitched together from the remains of everything it has ever consumed, and that includes the raw material that eventually became the sun, and the planets, and the carbon in your cells and the iron in your blood. There is a strange comfort available here, if you look for it, and I want to offer it before the fear closes back in, because both are true at once. The consuming and the building are the same process. The Milky Way is a predator, yes, but it is also a cradle, and it became a cradle precisely by being a predator. Without those long billions of years of merging and absorbing, gathering material from the galaxies it devoured, our galaxy would never have grown large enough or full enough of the heavier elements cooked up over generations of stars to make a world like the Earth or a chemistry like yours. You exist because the Milky Way ate. The same violence that erases the identities of consumed galaxies is the violence that, over unthinkable spans of time, gathered together the ingredients for you. It does not make the erasure less final, but it does mean that predation and creation, out here on these timescales, turn out to be two names for one act, which is a pattern we're going to keep meeting tonight, this refusal of the universe to keep its beauty and its terror in separate rooms. So here is where entry number 9 leaves us. Our home is a predator, built from the corpses of the galaxies it consumed, and destined itself to be consumed into something larger and stranger. That is unsettling in a way the first entry was not, because it is closer to us. It is not one weird class of distant stars, it is the ground we stand on, the sky we were raised under, revealed to be far less permanent and far less peaceful than it looks. But at least the Milky Way is something we can see. It is a great bright thing, mapped and measured and understood in its broad shape. The next entry on our list is not like that. The next thing we have to talk about is a kind of object that gives off no light at all, that we cannot see even when it is close, that could be crossing the space between the stars right now, moving through our galaxy in complete silence and complete darkness, and we would have almost no way of knowing it was there until it was already too late to matter. Part 3. Number 8. The predators with no light. Everything we have talked about so far we could at least see. The zombie stars we found by studying the light of their explosions, the galactic cannibalism we read in the streams of stars stretched across the sky. Light was our witness, but now we come to a kind of object whose entire horror is that it gives us no witness at all. A black hole on its own, adrift in the dark between the stars, emits no light whatsoever. And I do not mean that it is dim, or hard to see, or far away. I mean that light cannot escape it, and unless it happens to be actively pulling in glowing gas, there is quite literally nothing coming off of it for your eyes or our telescopes to catch. It is a piece of pure darkness moving through the dark. These are the rogue black holes, and they may be the closest thing the universe has to a genuine ghost. To understand where they come from, you have to picture the death of a very massive star, one many times heavier than our Sun. When such a star exhausts its fuel, its core collapses and the outer layers detonate in a supernova. If the core is heavy enough, nothing can stop its collapse, and it folds down into a black hole, a region where gravity has become so extreme that not even light can climb back out. Now, in an ideal, perfectly symmetric explosion, that black hole would simply sit where the star used to be. But real supernovae are almost never perfectly symmetric. The explosion tends to be lopsided, blasting more material out one side than the other, and just as a boat is pushed backward when you throw something forward off the bow, the newborn black hole is kicked in the opposite direction. Astronomers call this a natal kick, a birth kick, and it can be violent enough to hurl the black hole out of the crowded region where it was born, sometimes with enough speed to escape the gravitational grip of its entire galaxy. Once it has been kicked loose, the black hole becomes a wanderer. It has no companion star, no glowing disk of gas around it, nothing to announce its presence. It simply drifts through interstellar space, following whatever trajectory its birth kick gave it, silent and utterly invisible, and some of them are moving astonishingly fast. Certain rogue black holes are thought to travel at speeds exceeding 1.5 million kilometers per hour. Try to hold that in your mind. A region of collapsed space containing several times the mass of the Sun, folded down into an object only a few kilometers across, racing through the galaxy faster than anything in your experience, and doing it in perfect darkness and perfect silence. I want you to come with me for a moment and ride alongside one of these things, because the experience is not what you would expect. There is no roar, no glow, no sense of a monster approaching. If you were somehow floating out there in the distant space between stars, and one of these rogue black holes were passing nearby, you would see nothing directly at all. What you would notice, if you were looking very carefully, is something almost delicate. The stars behind it would begin to move. As the black hole drifts across your field of view, the faraway stars sitting behind it would smear and slide and bend, their light warped by the black hole's gravity into arcs and rings, dragged out of place and then released as it moved on. It would look, for a moment, as though a lens made of nothing were gliding across the sky, distorting the background like heat rising off a road. And then it would be past, and the stars would settle back into their places, and the darkness would close up again behind it, and you would have no way of knowing how close it had come. That is the entire signature. A brief bending of distant light, and then nothing. There is a strange dignity to how quietly these objects keep their secret. A star announces itself with light. A galaxy blazes with the combined glow of its billions of suns. Even a distant explosion sends its brightness racing across the cosmos to tell us it happened. But a rogue black hole does none of this. It has folded in on itself so completely that not even light can climb out of it, and so it moves through the universe having severed every ordinary line of communication. If you wanted to design the perfect hidden thing, a presence that exists and acts and yet betrays nothing of itself, you could hardly do better than a lone black hole in the dark between the stars. And the universe did not design it that way on purpose. It simply falls out of the physics, an ordinary consequence of a heavy enough star dying and being kicked loose. The most perfectly hidden objects in creation are not the product of any concealment. They are just what happens sometimes when a star ends. That bending of light is not just a poetic image, by the way. It is exactly how the first strong candidate for one of these objects was actually found. In the year 2022, astronomers announced the detection of an isolated dark object in our galaxy, spotted through a technique called gravitational microlensing. What they had observed was precisely the effect I just described. A compact invisible mass had passed almost directly in front of a distant background star, and its gravity had briefly bent and magnified that star's light in a very particular, predictable way. There was nothing to see where the mass itself was, only the fingerprint it left on the light coming from behind it. And here is the part that should give you pause. This object was found essentially by chance, because it happened to line up with a background star from our point of view. The discovery being an accident tells you something chilling. If they are only detectable when they happen to pass in front of something bright, then for every one we catch, countless others must be moving through the dark unseen, never lining up with anything, never leaving a trace. I should be honest with you, because intellectual honesty matters, and because the truth here is interesting in its own right. In the case of that 2022 detection, astronomers debated exactly what the object was. Some analyses suggested it was a black hole, others that it might be a neutron star, another kind of ultra-dense stellar corpse. The measurement sat right at the boundary between the two possibilities. But that uncertainty does not soften the underlying point, it sharpens it. Whether that particular object was a black hole or a neutron star, we know that both exist, we know that supernovae can kick them loose, and we know that they can wander the galaxy invisibly. The debate over one object only underlines how little we can say for certain about the population as a whole, and that population may be enormous. Astronomers estimate that our galaxy could contain up to around 100 million wandering stellar mass black holes, drifting along their own private trajectories through interstellar space. 100 million invisible predators, each one a piece of folded darkness, each one following a path that is, for all practical purposes, unpredictable. We do not have a map of them. We cannot have a map of them, because we cannot see them. They are the definition of the thing you would never see coming. Now, I do not want to frighten you unnecessarily, so let me be clear and calm about the actual risk. Space is overwhelmingly empty, and the chance of one of these objects coming anywhere near our solar system in any span of time that matters to us is extraordinarily small. This is not something to lie awake worrying about, but the reason it belongs on this list is not the probability. It is the nature of the threat. Because if one of these rogue black holes ever did drift into the outer reaches of our solar system, it would not need to strike the Earth or come anywhere close to it to be catastrophic. Its gravity alone, passing through the outer edges where the comets live, could be enough to unmoor planetary orbits and to fling a rain of comets and debris inward toward the inner planets. And the truly disturbing part is the warning we would get, which is almost none. A rogue black hole gives off no light, no heat, no radio signal, nothing. We would not see it approaching. The first sign that something was wrong might be the slow, wrong drift of the outer planets, the subtle disturbance of orbits that had been stable for billions of years, as an invisible mass reached in and began to rearrange the furniture of our cosmic home. This is the third thread, and it is the one that will sound loudest through the rest of tonight. The zombie stars broke the rule that death is final. The galactic cannibalism broke the rule that home is permanent, and the rogue black holes break something subtler and, I think, more frightening. They break the assumption that we would at least know. We comfort ourselves, without quite realizing we're doing it, with the idea that a real threat would announce itself, that we would see the monster coming and have time to feel afraid. The rogue black hole takes that comfort away. It is the thing that arrives without a herald, the danger with no face and no sound, the predator you would never see coming until it was already reaching into your world. Let me sit for a moment longer with the sheer strangeness of an object that gives off no light, because I think we underestimate how deeply unsettling that really is. Almost everything we know about the universe we know through light. Our eyes evolved to catch it. Our telescopes are built to gather it. Our entire science of the cosmos is, at bottom, the careful reading of light that has travelled to us across space and time. Light is how the universe speaks to us. It is the one messenger that reaches across the emptiness and tells us what is out there. And a rogue black hole is a thing that has stepped entirely outside that conversation. It sends no message, it reflects nothing, emits nothing, announces nothing. It is a piece of the universe that has gone completely silent, that exists but does not communicate its existence, and in a cosmos where we depend on light for absolutely everything we know, an object that refuses to give off any light at all is close to the definition of the unknowable. And consider what that means for the numbers. When astronomers estimate that there might be up to 100 million of these wandering black holes in our galaxy, that estimate is not built on a census, because a census is impossible. You cannot count things you cannot see. It is built on inference, on models of how many massive stars have lived and died and been kicked loose over the history of the galaxy. Which means the true number could be different, and we would have no direct way to check. There could be a rogue black hole passing through the outer reaches of our own solar system, right now, tonight, and unless it happened to line up perfectly with a background star and betray itself through the bending of light, we would have no way of knowing. I do not say that to frighten you, because again, the space is so large, and these objects so comparatively few, that the odds of any close encounter are extraordinarily small. I say it because it is a clean and honest example of something that runs underneath this entire list. The universe is full of things we cannot see, and our sense of safety rests, more than we like to admit, on the simple fact that we have not noticed them. Hold that phrase. You would never see it coming. Because we are going to meet it again tonight, in larger and larger forms. The rogue black hole is invisible, but it is at least small, a single object of stellar mass moving through the dark. The next thing on our list is not distant and not small and not other. The next thing is the star at the centre of your own sky, the one you were taught to think of as the steady, dependable, life-giving source of everything good. Our own sun, it turns out, is keeping a secret about what it is capable of, and the evidence for that secret was hiding, of all places, inside the rings of ancient trees. Part 4, Number 7. The fire our own sun hides. So far, every terrifying thing on our list has been comfortably far away. Dying stars in other galaxies, predators drifting somewhere out in the dark. It is easy to hold that kind of fear at arm's length, because it lives out there, among the distant lights. But now I have to bring the danger home, all the way home, to the one star you depend on for every heartbeat of your life. Because the sun, that warm and steady presence that has risen every morning of your existence, that feels like the very definition of reliability, harbours a capacity for violence that most people never learn about. And what makes this one so unsettling is not that the sun is a distant monster. It is that the sun is the opposite of distant. It is the source of everything, and it holds a switch that, if it were ever thrown, we could not stop and could barely survive. The story of how we learn this is one of the strangest detective tales in modern science, and it begins not with a telescope but with trees. In the year 2012, a Japanese researcher named Fusa Miyake and her colleagues were studying the growth rings of ancient trees. Each ring records a year, and locked inside each ring is a chemical record of the atmosphere at the time it grew. What they found, in the rings corresponding to the years 774 and 775 of the Common Era, was a sudden sharp spike in a particular form of carbon, the kind that gets created when a burst of high-energy radiation slams into the upper atmosphere. The spike was enormous, far larger than anything the ordinary sun produces. Something had struck the Earth more than 1,000 years ago, with a blast of radiation many times more powerful than any solar event ever recorded in the modern age of instruments. The best estimates put it at roughly 20 times stronger than the most powerful flares we have measured directly. And it was not a fluke. When researchers went looking, they found evidence of similar events at other points in history, spikes buried in tree rings and in the layered ice of glaciers, suggesting that these enormous solar outbursts, now often called Miyake events, recur on something like a once-in-1,000 years rhythm. There was another around the year 993. These are not gentle stellar hiccups. A solar superflare of this kind releases energy on a scale that is genuinely difficult to put into human terms, the equivalent of billions of the most powerful nuclear weapons detonating on the sun at once, hurling radiation and charged particles across the 93 million miles of space between the sun and the Earth. To understand what such an event would do to us, it helps to look at a much smaller one that we did witness, and that we still talk about with a kind of wonder. In the year 1859, the Sun unleashed a powerful storm now known as the Carrington event, after the astronomer who watched the flare erupt. When the wave of charged particles reached the Earth, it lit up the sky with auroras seen close to the equator, and it wreaked havoc on the most advanced technology of the day, which was the telegraph. Telegraph systems failed, sparks leapt from the equipment, and in some cases the electrical currents induced in the wires were so strong that operators found they could send messages with their power sources disconnected entirely, the lines carrying current supplied by the storm itself. Some telegraph paper reportedly caught fire, and that was a storm far weaker than the ancient superflares hiding in the tree rings. Now transplant an event like the Carrington storm, or worse, one of the far larger Miyake-scale superflares, into our modern world, and the picture becomes genuinely sobering. We have wrapped our entire civilization in delicate electronics and immense networks of power lines, and those are exactly the things a great solar storm attacks. The surge of energy could overload and destroy electrical grids across whole continents, and the largest transformers, the ones that take many months or years to build and replace, could be burned out on a scale we have no capacity to repair quickly. Satellites, on which we depend for navigation, communication and timing, could be crippled or destroyed. Every electronic device on the facing side of the planet could be at risk, and any astronauts in space outside the protective cocoon of the Earth's atmosphere and magnetic field could receive a lethal dose of radiation within minutes. I want to tell you about a moment that should have received far more attention than it did, because it turns this from a historical curiosity into a present-tense fact. In the year 2012, the same year the tree ring discovery was published, the Sun launched an enormous eruption, a coronal mass ejection comparable in power to the Carrington event. It tore across space and passed directly through the orbit of the Earth. The only reason it did not strike us is timing. The eruption crossed the point in Earth's orbit that our planet occupies just about a week after the Earth had been sitting in that exact spot. We missed a civilization-scale solar storm by a matter of days, not by careful planning, not by any defense we mounted, but by the sheer luck of orbital timing. Had the Earth been a week further along in its journey around the Sun, you might be listening to this in a very different world. I find it worth sitting with the idea that our sense of the Sun's reliability is, in a way, a trick played on us by the shortness of recorded history. For the few thousand years that humans have kept careful records, the Sun has been remarkably well behaved. It has risen and set, warmed the seasons, thrown the occasional modest storm, and otherwise behaved like the dependable presence we take it to be. And so, we built a picture of the Sun as a calm and steady star, and we built our entire civilization on the assumption that this calm is simply what the Sun is. But a few thousand years is nothing to a star. The Sun is more than 4.5 billion years old. Judging the Sun's temperament from human history is like judging the temperament of the ocean by watching it for a single quiet afternoon and concluding that it never storms. The tree rings and the ice cores extend our memory back past the reach of human record-keeping, and the moment they do, the storms appear. The Sun has thrown its great furies before, more than once, in the years before anyone was writing anything down. Our impression of a perfectly gentle star is not wrong exactly. It is just far too short-sighted, built on a slice of time so thin that the rare and violent moments simply have not happened to fall inside it yet. And there is a larger context that makes it all the more humbling. When astronomers turn their instruments on other stars similar to our Sun, ordinary middle-aged sun-like stars, they see something disquieting. Those stars are capable of producing superflares thousands of times more powerful than anything we have ever recorded from our own Sun in the modern era, up to 10,000 times more powerful in some cases. Our Sun appears, from what we can tell, to be relatively calm as sun-like stars go. But the ancient tree rings tell us that even our calm star has its rare moments of fury, and the physics that lets other stars flare so violently is the same physics operating inside our own. Here is the thread again, and notice how it has changed shape. With the rogue black holes, the fear was that we would never see the threat coming. With the Sun, the fear is different and in some ways worse. We can see the Sun. We watch it constantly, with a fleet of spacecraft dedicated to studying it. We would very likely see a superflare erupt, but seeing it would not save us. The warning we would get from the moment of eruption to the arrival of the storm would be measured in hours, perhaps a day or two at most, and in that handful of hours there is very little we could actually do. We cannot shield the entire planet's electrical grid. We cannot armor every satellite. We cannot prevent the radiation from arriving. The most unsettling thing about a solar superflare is not that it is hidden, but that it is essentially unstoppable. Our technological civilization, for all its apparent strength and sophistication, exists entirely at the mercy of the moods of a star we did not build and cannot control. There is a quiet dependence here that we almost never think about. Every part of modern life, the food that arrives in cities, the water that flows from taps, the medicine kept cold, the money that exists as numbers in machines, the communication that ties the world together, all of it rests on a thin, invisible web of electricity and electronics, and that entire web is vulnerable to the temper of the sun. We have built a civilization of extraordinary complexity on the assumption that our star will keep behaving the way it has behaved during the brief window of recorded history. The tree rings tell us that assumption is not quite safe. The sun has thrown these enormous flares before, roughly once a millennium, and it has been more than 1,000 years since the last of the truly great ones. I want to dwell for a moment on why the tree rings and the ice cores are able to tell us this, because the method itself is quietly beautiful, and it turns the whole planet into a kind of ancient recording device. When a powerful blast of radiation from the sun strikes the upper atmosphere, it slams into the nitrogen up there and triggers the creation of a heavier, radioactive form of carbon. That carbon drifts down, gets taken up by growing plants, and becomes locked into the wood a tree lays down that year, and into the layers of ice building up in glaciers. So each ring of an old tree, each thin band of ancient ice, holds a faint chemical fingerprint of how much radiation was arriving from space when it formed. Nobody set out to record the tempers of the sun across 1,000 years. The trees and the glaciers did it anyway, silently, just by living and freezing. And when researchers finally learned to read that record, they found the sun's rare furies written there, in years long before any human instrument existed to measure them. The planet had been keeping a diary of solar violence all along, and we only recently learned the language. And there is a sobering asymmetry I want to name plainly, because it is the real reason this entry belongs on a list of terrors rather than a list of curiosities. In 1859, when the Carrington storm struck, the most vulnerable technology on Earth was the telegraph, a thin web of wires that could fail without threatening a single life directly. Our ancestors experienced that storm as a strange and beautiful night of glowing skies and sparking equipment, and then they moved on. But in the century and a half since, we have woven electricity and electronics into the foundation of everything. We have built a civilization that cannot feed itself, cannot move water, cannot keep medicine cold, cannot communicate across a city without a continuous supply of electrical power flowing through delicate systems. We have, in other words, become far more powerful and far more fragile at the same time. The very same solar storm that our ancestors survived as an inconvenience could, arriving today, unravel the basic machinery of modern life across whole continents. We did not become safer as we advanced. In this one specific and important way, we became more exposed, and we did it without noticing, because the sun has been quiet during the brief window in which we built all of it. So entry number 7 brings the fear home in the most intimate way yet. The thing you were taught to think of as the very symbol of warmth and dependability, the giver of all light and life, is also the object most capable, on any timescale that matters, of throwing our entire civilization back into a pre-electrical age, and there is essentially nothing we could do to prevent it. The calm, golden, familiar sun is not a lie, exactly. But it is only part of the truth, and the rest of the truth was hiding for over 1,000 years inside the silent rings of trees. And yet, for all its power, the sun is close, and it is bright, and it is understood. We know where it is, and what it is made of. The next entry retreats from that intimacy into something almost the opposite. We're going to leave the warmth of stars behind entirely, and travel out to a region of the universe defined not by what is in it, but by what is missing. A place so empty, so immense, and so profoundly, unsettlingly quiet, that if we happened to live inside it, we might have grown up believing that we were completely, cosmically alone. Part 5, Number 6, The Great Nothing. We're halfway through our list now, and I want to shift the character of the fear. Everything so far has been about presence. A star that would not die, a galaxy that eats, a predator in the dark, a fire in our own sun, things that are there, doing something. But some of the most unsettling things in the universe are defined not by presence but by absence, not by what they contain, but by what they are missing. And the sixth entry on our list is the greatest absence we have ever found, a region of space so immense and so empty that astronomers, who are not usually given to dramatic language, quietly began calling it the Great Nothing. Its formal name is the Boötes Void, named for the constellation Boötes, the herdsman, in whose direction it lies. It was discovered in the year 1981 by the astronomer Robert Kirshner and his colleagues, and the way they found it is telling. They were conducting a survey, mapping the positions of galaxies across a patch of sky, building up a three-dimensional picture of where things were. And in the middle of their data, they found a hole. Not a hole in the sky, not a dark patch, but a hole in the distribution of galaxies, a region where the galaxies they expected to find simply were not there. At first, a gap like that looks like a mistake, a place where the survey missed something, but the gap held up. It was real. They had found an enormous, nearly spherical region of space that was almost completely empty. The scale of this emptiness is where it stops being a curiosity and starts becoming something you feel in your chest. The Boötes Void is roughly 330 million light-years across. Its centre lies about 700 million light-years from Earth. To cross it at the speed of light, the fastest anything can travel, would take 330 million years. And within that colossal volume, astronomers have found fewer than about 60 galaxies. That number lands differently when you know what it should be. Based on the average density of galaxies in the universe, a region that size should contain something on the order of 10,000 galaxies. Instead, it holds a few dozen. It is roughly 80 to 90% emptier than it has any right to be. If you took the ordinary universe and scooped out almost everything, you would get the Boötes Void. To understand why that is so strange, you have to know that the universe, on the larger scales, is not smooth. It has a structure, and the structure is beautiful. Galaxies are not scattered randomly. They are strung together along immense filaments and sheets, like a three-dimensional cobweb, or the foam of soap bubbles, with galaxies gathered along the surfaces and edges and great empty spaces in the hollows between. So the universe does have voids. Emptiness is actually the normal state of most of cosmic volume. But even ordinary voids contain some scattered galaxies, a few threads of matter passing through. The Boötes Void is extreme even by the standards of voids. It is not just large, it is unusually, almost aggressively empty, as though something had swept nearly all the matter out of an enormous sphere and left it hollow. And there is the shape. Natural structures in the universe tend to be irregular, lumpy, shaped by the messy interplay of gravity pulling matter this way and that. But the Boötes Void is strikingly close to spherical, a great round emptiness, and that regularity has puzzled astronomers since it was found. The leading and most sensible explanation is that the Boötes Void is not one void but several. That long ago a number of smaller voids sat near one another, and as the universe expanded and matter drained away from underdense regions toward denser ones, those smaller voids merged and grew and coalesced into one gigantic emptiness. There is even a hint of this in the data, a thin thread of galaxies running through part of the interior, which some read as a kind of fossil seam, the leftover boundary where smaller voids once met. It is a good explanation. But it still strains to fully account for both the sheer size and the sheer emptiness at the same time. Now I want to arrive at the thing about the Boötes Void that I find genuinely haunting. More haunting than any explosion or predator we have discussed, because it is quiet and because it is about us. The astronomer Greg Aldering once framed it in a way that has stayed with everyone who has heard it. He pointed out that if the Milky Way were located at the centre of the Boötes Void, we would not have known that other galaxies existed until the 1960s. Think carefully about what that means. Our nearest galactic neighbours would be so far away, across that immense emptiness, that they would have been invisible to us until our telescopes became powerful enough, only a few decades ago, to just barely make them out. For almost the entire history of human astronomy, we would have looked out into the night and seen our own galaxy and nothing beyond it, and we would have concluded reasonably carefully, using the best evidence available to us, that our galaxy was the whole universe, and that we were utterly alone. Sit with that for a moment, because it is the core of tonight's deeper fear. Imagine a civilization living at the centre of such a void. Imagine their astronomers, as careful and as brilliant as ours, building their telescopes, measuring their skies, developing their theories. And imagine that every single one of them, across their entire history, is confidently, rigorously, and permanently wrong about the most basic fact of existence. The fact that they are not alone, that the universe is filled with hundreds of billions of galaxies, that they are one small light among an ocean of others. They would never know, not because they were foolish, not because they failed to look, but because the truth simply could not reach them. The light carrying that truth would be too faint, too far, too long in coming. They would be sealed inside their emptiness, doing everything right, and still living inside a false picture of the universe, with no way even to suspect it. And here is why that should unsettle you gently on a night like this. It raises a question we cannot fully answer about ourselves. We do not live at the centre of the Bhuta's void, as far as we can tell. But how sure can we ever be about what we cannot see? Our entire confident picture of the cosmos is built on the light and information that happens to be able to reach us. And if a whole civilization could be trapped in emptiness, careful and wrong, then the deepest fear the Bhuta's void offers is not about that void at all. It is about the possibility that our own certainty is also shaped, and perhaps quietly limited, by an accident of where we happen to stand. The calm night sky, once again, is a report on our eyes. The Bhuta's void is simply the most extreme demonstration of how much that report can leave out. There is a further layer to the void that deepens the unease, and it has to do with what the emptiness might be teaching us, if we are humble enough to listen. The universe is not made only of the matter we can see. It is dominated by things we cannot, the mysterious dark matter that outweighs ordinary matter several times over, and the even more mysterious dark energy that appears to be driving the accelerating expansion of everything. Voids like Bhuta's are, in a strange way, some of the cleanest laboratories we have for studying those invisible ingredients, precisely because they are so empty. In a region with almost no ordinary matter cluttering the view, the subtle effects of dark energy and the behavior of the cosmic web become easier to isolate. So the greatest emptiness we have ever found is not just a frightening absence. It is also a window, one of the few places clear enough to let us make out the invisible scaffolding on which the whole universe is built. The nothing, it turns out, has something to say. And I keep coming back to the loneliness of it, because that is the part that lingers after the numbers fade. We have spent this list so far among crowded, violent things, stars packed with fire, galaxies grinding together, engines blazing. The Bhuta's void is the opposite of all that. It is what a large portion of the universe actually looks like, hollow and quiet and nearly starless, and it reminds us that the busy, companionable sky we know is the exception, not the rule. Most of the cosmos is emptiness. The filaments and clusters where galaxies gather, the bright crowded places like the one we happen to live in, are thin, bright threads strung through a darkness that vastly outweighs them. We were born in one of the rare crowded corners, and so we grew up imagining that crowding is normal. But if you could see the universe as it truly is, at its largest scale, you would see mostly void, with the light gathered into a delicate lacework running through an ocean of nothing. The Bhuta's void is simply that ocean, made visible in one enormous, undeniable sphere. This is the fifth thread, and it is the one that will carry us into the strangest territory of the whole list. What force or event could carve out an emptiness 330 million light-years wide? And if nature can produce regions of such perfect nothing, how confident can we really be that we are reading the rest of the universe correctly? The Bhuta's void does not threaten us with violence. It threatens us with something quieter and I think more profound. It threatens our confidence that we know where we are and what surrounds us. But we're only halfway. And now the list turns back toward violence, toward objects so extreme that they make everything we have discussed feel almost gentle, because we have talked about emptiness, and about our own vulnerability, and about the limits of what we can see. Now we return to the small and the dense and the unimaginably powerful. The next entry is an object no larger than a city, and yet it carries the most intense magnetic field in the entire known universe. A field so strong that its effects were once felt here, on Earth, from 50,000 light-years away, on a single night in December, in a way that briefly touched the air above our heads. Part 6. Number 5. The Magnetic Monsters. There is a category of object in the universe so extreme that even seasoned astronomers, when they describe it, reach for language that sounds like exaggeration, and then have to remind you that they are being literal. That object is the magnetar, and it sits at number 5 on our list because it holds a record that is almost impossible to comprehend. It possesses the strongest magnetic field known to exist anywhere in the universe. And unlike the emptiness of the void or the invisibility of a rogue black hole, the power of a magnetar is not abstract. On one night, more than 20 years ago, we felt it here, in the atmosphere above our own planet, from a distance of 50,000 light-years. To build a magnetar, you first have to build a neutron star, which is already one of the most extreme objects nature makes. When a massive star dies and its core collapses, and if that core is not quite heavy enough to become a black hole, it collapses instead into a neutron star, an object where the crush of gravity has forced matter into a state so dense it defies imagination. Take more than the entire mass of our Sun, and compress it into a sphere only about 20 kilometers across, roughly the size of a city. The density becomes staggering. A single sugar cube-sized piece of neutron star material would weigh as much as a mountain. This is already a monster. But a magnetar is a neutron star with one additional feature turned up to an impossible degree: its magnetic field. The Earth has a magnetic field. It is the thing that makes a compass needle swing to the north, the thing that shields us from much of the sun's radiation, and it is gentle enough that we live our entire lives without feeling it. A magnetar's magnetic field is roughly 1 quadrillion times stronger than the Earth's. A quadrillion is a one followed by 15 zeros. I could say that number 100 different ways and it would not become imaginable, so let me instead tell you what such a field would do. If a magnetar appeared at the distance of the Moon, its magnetic field would be strong enough to wipe every credit card and erase every hard drive on Earth, and to disturb the metals in your body. Come closer, and the effects become lethal in ways that are difficult to even describe. Within about 1,000 kilometers of a magnetar, its magnetic field would be so intense that it would begin to distort the very atoms of your body, deforming the electron clouds that hold your molecules together, unmaking your chemistry from the inside. You would not be crushed or burned in any ordinary sense. You would simply cease to be able to exist as an arrangement of atoms, because the field would not permit atoms to hold their normal shapes. Now, these objects are not gentle in their behavior either. A magnetar's magnetic field is so powerful that it puts the star's own solid crust under unbearable strain, and every so often that strain becomes too much, and the crust of the neutron star fractures in an event astronomers call a starquake. When it happens, the magnetar releases a sudden violent burst of gamma rays and X-rays, an eruption of energy on a scale that is hard to place in any human frame of reference. Let me take you to one such moment, because it actually happened, and because we recorded it. The date is the 27th of December, in the year 2004. Far across our galaxy, at a distance of about 50,000 light-years, there is a magnetar catalogued with the designation SGR 1806. On that day, its crust fractures. In a fraction of a second, a tenth of a second, this single object releases more energy than our Sun produces in 100,000 years. The burst races outward across the galaxy at the speed of light, crossing 50,000 light-years of space, and it arrives at the Earth. And even after travelling that unimaginable distance, even after 50,000 years in transit, it is still strong enough to matter. It briefly outshines the full moon in gamma rays. It measurably disturbs the upper layers of Earth's atmosphere, the ionosphere, ionizing the air above our heads, from an object so far away that its light left before human civilization existed. We were not harmed, but we were touched. A starquake on a city-sized object halfway across the galaxy reached down and brushed the air above our planet. Let that arrive fully, because it is the point of this entry. Astronomers calculated that if that same burst had occurred within about 10 light-years of the Earth, close in galactic terms but still far beyond our nearest star, it could have triggered a mass extinction. The radiation would have been enough to devastate the ozone layer and irradiate the surface of the planet. And the thing that produced it is not rare in the grand scheme and not predictable at all. There are about 30 confirmed magnetars in our Milky Way, and there are almost certainly many more that we have not detected, because they spend most of their time quiet, only revealing themselves in these sudden, random, unpredictable eruptions. They are silent for years, and then, without warning, one of them fractures, and space around it is briefly bathed in enough radiation to sterilize any world in the neighborhood. It is worth pausing on the fact that a magnetar is only about 20 kilometers across, because that number does something strange to the mind when you hold it against everything else we have said. 20 kilometers is nothing. It is the size of a city, a thing you could drive across in a matter of minutes, and yet packed into that small sphere is more mass than our entire sun, spun up and wrapped in a magnetic field of a power that exists nowhere else in the known universe. The most extreme magnetism in all of creation is not housed in something enormous. It is housed in something tiny, something you could lose against the face of a planet. This is one of the quiet lessons the universe keeps teaching us, that the most concentrated power is often found in the smallest packages, that a thing the size of a city can reach across 50,000 light-years and stir the air above our heads. Size and danger, out here, have almost nothing to do with each other. The gentlest-looking star can hide a monster, and the monster, when you finally find it, can be smaller than the town you live in. Here is our recurring thread, and see how it deepens. With the rogue black hole, the horror was that you would never see it coming. The magnetar is a variation on that same theme, but stranger. We can see magnetars. We know roughly where the ones near us are, but we cannot predict them. A magnetar gives no warning before a starquake. There is no build-up we can detect, no countdown, no swelling that tells us an eruption is near. It is quiet, and then it is not, and by the time the burst reaches us, it has already been travelling for tens of thousands of years, arriving from an event that finished before the light we are seeing even set out. The danger is not hidden from us. It is simply beyond our power to anticipate, which in the end amounts to the same helplessness. And there is that phrase again, the one I asked you to hold. You would never see it coming. Not because the magnetar is invisible, but because its violence is instantaneous and its timing is beyond us. We already live within the reach of these objects. The night of December 27th, 2004 proved it. We are not safely separated from the most extreme magnetic forces in the universe by any wall or shield. We are simply separated by distance, and distance, as we keep discovering tonight, is a thinner protection than it feels. There is something almost humbling in how casually this power operates. The magnetar that touched our atmosphere in 2004 was not aiming at us. It did not know we were here. It simply fractured as magnetars do, and released a fraction of a second of energy that happened to wash over our world on its way out into the larger dark. We were incidental, and that, I think, is the quiet lesson underneath all of this. The most extreme forces in the universe are not malicious. They are simply indifferent, operating on scales of energy and distance, where a whole planet full of life is not even a rounding error, where the difference between touching our atmosphere and ending all life on Earth is nothing more than the accident of how far away the object happens to sit. I want to give you a way to hold just how absurd a magnetar's magnetism really is, because the number, 1 quadrillion times the Earth's field, is too large to feel. Physicists sometimes describe it this way. The magnetic field of a magnetar is so intense that it does not merely push on things, it reshapes the empty space around it and the atoms within it. In an ordinary atom, the electrons are held in roughly spherical clouds around the nucleus. But in a field that strong, those clouds would be squeezed into thin, needle-like shapes, aligned with the field, distorting the very structure of matter. Chemistry as we know it, which depends on the ordinary shapes of atoms, would simply cease to function. There is a region around a magnetar where the concept of a normal atom breaks down entirely, where matter is forced into forms that exist nowhere else in the universe except around these objects. It is not that a magnetar would hurt you. It is that within a certain distance you could not exist as you, because the rules that let your atoms hold together would no longer apply. And here is a thought that I find quietly staggering, one that ties the magnetar back to everything else we have discussed. This object, capable of unmaking matter, capable of reaching across 50,000 light-years to brush our atmosphere, is a corpse. It is what remains after a star has already died. Everything violent about a magnetar, the crushing density, the impossible magnetism, the sudden starquakes, is the afterlife of a star that ended long ago. The living star that made it was enormous and bright and ordinary in its way, and only in dying did it collapse into this small, dense, monstrous thing. We tend to imagine that death, in the universe as in life, means quieting down, cooling off, fading away. The magnetar says otherwise. Sometimes death is not an ending but a concentration, a folding of all a star's power into a smaller and fiercer form. The most extreme magnetic objects in existence are not living stars at all. They are the graves of stars, and the graves, it turns out, are far more dangerous than the living ever were. So we have met the strongest magnets in creation, city-sized corpses of dead stars whose reach already extends to our doorstep. But a magnetar, for all its violence, is still a small thing, a single collapsed star. The next entry abandons that scale entirely, because now we come to the objects that do not merely touch a distant atmosphere, but that can outshine entire galaxies, that pour out more light than 100 trillion suns from a region no bigger than our solar system, and that fire beams of destruction across distances so immense they dwarf the width of the Milky Way itself. And the most unsettling part of what comes next is that the same kind of engine, quiet now and sleeping, sits at the very centre of our own galaxy, waiting for a reason to wake. Part 7. Number 4. The brightest engines in creation. In the year 1963, an astronomer named Martin Schmidt was puzzling over a faint blue point of light. It had been catalogued as a kind of star, an unremarkable smudge given the designation 3C273. But when Schmidt studied its light carefully, breaking it apart into its spectrum, he realized he was not looking at a star at all. He was looking at something that should not have been possible. The object was enormously far away, billions of light-years distant, and for it to appear as bright as it did from that distance, it had to be pouring out a staggering amount of energy. It was outshining an entire galaxy of hundreds of billions of stars, and yet all of that light was coming from a region of space no larger than our solar system. Schmidt had found the first of what we now call quasars, and their discovery revealed a level of raw power that astronomers had, until that moment, thought impossible. The name quasar is a compression of an old clumsy description, quasi-stellar radio source, which just means an object that looked like a star but clearly was not one. And once astronomers understood what was actually powering these things, the picture became both clearer and far more frightening. At the centre of a quasar sits a supermassive black hole, an object with the mass of millions, or even billions, of suns, and this black hole is feeding. Matter, gas and dust and torn-apart stars spirals inward toward it, and as it falls it forms an immense flattened swirling disk. The material in that disk is compressed and accelerated and heated by friction and gravity to temperatures of millions of degrees, so hot that it blazes across the entire spectrum of light, from radio waves to the most energetic X-rays. A quasar is, in essence, the light given off by matter in its final moments as it falls toward oblivion. It is the brightest sustained phenomenon in the entire universe. The numbers here strain the mind in the way that only cosmic numbers can. A typical quasar can shine with the brightness of more than 100 trillion suns. Hold those two facts side by side. More light than 100 trillion suns produced within a volume not much larger than the space between our own sun and its planets. It is as though someone took the combined output of many galaxies and concentrated it into a single point. And the source of all that light is not fusion, not the burning of fuel the way ordinary stars shine. It is gravity. It is the sheer violence of matter falling into a supermassive black hole. Quasars are the universe's demonstration that gravity, given enough mass to work with, can outshine every star in a galaxy combined. But brightness is not the most terrifying thing a quasar can do. Some of these objects produce something even more alarming, called relativistic jets. As matter spirals into the black hole, a portion of it is redirected and hurled back outward along the black hole's axis of rotation, focused into two narrow beams of particles, and radiation accelerated to very nearly the speed of light. These jets are not small. They can extend across distances that make the width of an entire galaxy look modest. One quasar, catalogued as PKS 0637, drives a jet that stretches for more than 1.5 million light-years. To give that a frame, our entire Milky Way galaxy is about 100,000 light-years across. This single jet, fired from one object, extends more than 15 times the width of our whole galaxy, and it carries enough energy that any galaxy unfortunate enough to lie in its path could be sterilized, its capacity to form and sustain life scoured away by a beam of radiation from a distant engine. There are quasars still burning today, though most belong to the early universe, when galaxies were younger and their central black holes had more matter within reach to devour. The nearest known quasar, an object called Markarian 231, lies about 581 million light-years from Earth. Its central black hole is consuming the equivalent of about 1,000 suns worth of material every single year, and producing enough radiation in the process to destroy any planetary system in its vicinity. When you look at a quasar, you are looking at a black hole not as a passive drain, not as the quiet, invisible predators we discussed earlier, but as an active furnace, the most luminous individual object the observable universe contains, a place where the act of destruction itself becomes the brightest light in creation. Now, I want to bring this home, the way I have been trying to bring each of these things home, because a quasar billions of light years away is easy to keep at a comfortable distance. Here is the part that should make you sit up. At the center of our own Milky Way galaxy, at the center of the galaxy you live in, there is a supermassive black hole. Its name is Sagittarius A star, and it contains about 4 million times the mass of the Sun. Right now, it is quiet. It is not feeding on much, and so it does not blaze. It sits at the center of our galaxy in relative darkness, a sleeping engine. But it is the same kind of object that powers a quasar. The only difference between the peaceful center of our galaxy and the blazing center of a quasar is fuel. A quasar is a supermassive black hole that is eating. Ours simply has not been offered a large enough meal in a long time. Consider, then, what it would mean if that changed. If a large cloud of gas, or a cluster of stars were to wander too close to the center of our galaxy and begin to fall inward, our own Sagittarius A star could awaken. It could form an accretion disk, begin to blaze, and turn the quiet center of the Milky Way into an active galactic nucleus, a quasar in its own right. Whether that would pose any direct danger to us, so far out here in the galaxy's suburbs, tens of thousands of light years from the center, is genuinely uncertain, and I do not want to overstate it. But the mere fact is enough. The same furnace that lights up the most violent objects in the universe sits, dormant, at the core of our own home galaxy. The engine is already installed. It is simply waiting for fuel. There is one more thing about quasars that I cannot leave out, because it folds the terror back into something close to gratitude. These blazing engines were far more common in the early universe than they are today, when galaxies were young and their central black holes had abundant matter within reach to devour. And that early violence, all those quasars pouring out radiation and driving enormous winds of gas out of their galaxies, actually helped to shape the universe we live in. The floods of energy from feeding black holes regulated how galaxies grew, heating and expelling gas, throttling the formation of new stars, sculpting galaxies into the shapes we see now. The same furnaces that could sterilize a world were also, on the larger scale, part of what made galaxies settle into stable, life-permitting maturity. Once again, the universe refuses to keep its violence and its creativity apart. The brightest, most destructive objects in existence were also, in their way, among the architects of the calm, ordered cosmos we were eventually born into. The furnace that frightens us is the same furnace that helped build the house. Here is our thread, and notice how it has quietly turned. For most of this list, the fear has come from outside, from distant objects and far-off events. But with the quasar, the fear folds inward. The most luminous, most destructive kind of engine in the universe is not only out there among the distant galaxies. A sleeping version of it lives at our own center, has lived there the whole time, through every night of human history. 4 million solar masses of collapsed space sitting quietly in the dark at the middle of our galaxy. We orbit it. We always have. The furnace sleeps at the center of our own sky. And that is the unsettling beauty of a quasar, the thing that makes it belong on this list. It is not just a distant monster. It is a preview of what the quiet things around us are capable of becoming. The invisible black holes we discussed earlier, the dormant giant at our galactic core, all of them are potential quasars, waiting only for enough matter to fall in. Destruction and brilliance in the universe turn out to be the same act seen from different distances, and the brightest light in all of creation is nothing more than the sight of matter dying. There is a detail about how quasars were first understood that I find genuinely moving, and it shows how a single measurement can overturn a picture of the world. When Martin Schmidt looked at the light of 3C273 and worked out how far away it was, the distance implied something that seemed impossible. For the object to be that far and still look that bright, it had to be producing more energy than anyone thought a single source could produce. The instinct at first was that there must be some mistake, that no object could really shine that hard. But the measurement held, and so astronomers were forced by the stubbornness of the data to accept that the universe contained engines far more powerful than they had imagined, and to go looking for what could drive them. The answer, the supermassive black hole, was itself so strange that many resisted it for years. Quasars did not just reveal a new kind of object, they forced physics to accept that the universe was more extreme than its imagination had allowed, and that is a pattern worth noticing, because it keeps happening. Again and again, the real universe turns out to be more, not less, than we were prepared to believe, and I want to make the scale of a quasar's light land in a way that a bare number cannot. When you look at a photograph of a distant quasar, you're often looking at a single point of light that outshines the entire galaxy surrounding it, hundreds of billions of stars, all of them together dimmer than the one bright point at the centre. The galaxy, with all its suns and worlds and whatever might live on them, becomes a faint halo around the blaze of a single feeding black hole. Now recall what that light actually is. It is not the warm glow of stars going about the business of shining. It is the light given off by matter in the last moments before it falls out of the universe forever, heated to a fever as it spirals toward the point of no return. A quasar is the brightest thing in creation, and it is bright because it is a place where matter is dying in enormous quantities, continuously, for millions of years. The most luminous object the universe can make is, at its core, a long and radiant act of destruction, and there is no way to separate the beauty of its light from the violence of its cause. But even a quasar, the most luminous object in the universe, shines steadily, over millions of years, a furnace that burns and burns. The next entry is different in a way that makes it, I think, the most purely frightening object on this entire list. Because the next thing we have to discuss does not shine steadily. It arrives in an instant without warning, releasing in a few seconds more energy than our sun will produce in its entire lifetime. It is the most violent kind of explosion the universe has produced since the Big Bang itself, and one of them, in the year 2022, reached across 2.5 billion light-years of space and disturbed the atmosphere of our planet. Part 8, Number 3, The Cosmic Snipers. The discovery of the third thing on our list happened by accident, and the accident is worth telling because it says something about the kind of universe we live in. In the 1960s, at the height of the Cold War, the United States launched a fleet of satellites called the Vela satellites, designed to watch for the gamma rays that a secret nuclear weapons test would produce. The satellites were looking down at the Earth for the flash of a forbidden bomb, but every so often they detected bursts of gamma radiation that were not coming from the Earth at all. They were coming from far out in space. Something out there, far beyond our planet, was releasing sudden, intense flashes of the most energetic form of light there is. The satellites built to catch human violence had stumbled onto a form of cosmic violence so extreme that it would take decades to understand. We now call these events gamma-ray bursts, and they are, quite simply, the most powerful explosions to have occurred in the universe since the Big Bang itself. I want to give you the number that defines them, and then I want to help you feel it, because the number alone is too large to mean anything. In a typical gamma-ray burst, in the span of just a few seconds, an object releases more energy than our sun will produce in its entire lifetime. Not in a year, not in a century. In its whole 10 billion year life, from birth to death, the sun will radiate a certain enormous quantity of energy. A gamma-ray burst releases more than that, in seconds. For those few moments, a single gamma-ray burst can outshine everything else in the visible universe combined, every star in every galaxy, all of it, from one point for one brief instant. It took until the 1990s for astronomers to work out what could possibly produce such a thing, and the answer is that gamma-ray bursts mark moments of cosmic birth and death fused together. The long bursts occur when a very massive star reaches the end of its life, and its core collapses into a black hole. As the black hole forms, it drives jets of material outward through the dying star at nearly the speed of light, and those jets, punching out through the star's surface, produce the burst. The short bursts come from something else, from the collision and merger of two neutron stars, those city-sized corpses we discussed earlier, spiraling together and colliding in a cataclysm that also forms a black hole. In both cases, a gamma-ray burst is, in a sense, the birth cry of a black hole, the announcement that a new region of collapsed space has just been born, screamed across the universe in the most energetic light there is. Let me take you to the moment one of these ignites, because I think you should feel it, not just know it. Somewhere in a distant galaxy, a massive star far larger than our Sun has run out of fuel. Its core, no longer able to hold itself up, collapses in less than a second, folding down into a black hole, and as it does, twin jets of matter erupt from the poles of the newborn black hole, drilling outward through the collapsing star at almost the speed of light. The jets punch through the star's surface and burst into space, narrow and focused and unimaginably violent. For a few seconds, this single dying star pours out more light than all the other stars in the universe combined, and that light travels outward in a tightly focused beam, a searchlight of gamma radiation aimed in whatever direction the jets happen to point. If you are standing anywhere along that beam, even from across the width of the cosmos, it arrives with no warning at all. There is no swelling, no build-up, no herald. The star was there, and then the beam is upon you, having crossed billions of years of space to find you in a single silent instant. And that is what makes a gamma-ray burst the purest expression of a fear we have been circling all night. Because a gamma-ray burst is directional. It does not spread its energy evenly in all directions like an ordinary explosion. It concentrates it into those narrow beams, which means the danger is not just the power of the burst, but the aim. If a gamma-ray burst were to occur within our galaxy, and if one of its beams happened to be pointed directly at the Earth, the consequences would be severe even from thousands of light-years away. Models suggest that a burst aimed at us from within about 3,000 light-years could strip away a significant part of our ozone layer, the thin shield that protects the surface of the Earth from the Sun's ultraviolet radiation. With the ozone damaged, that ultraviolet light would pour down onto the surface, devastating the base of the food chain, the tiny organisms in the oceans, and cascading upward through every living thing. Some scientists have proposed, though it remains unproven, that a gamma-ray burst may have been responsible for one of Earth's ancient mass extinctions, the late Ordovician event of about 440 million years ago, which wiped out roughly 85% of marine species. Here is the phrase again, and here it reaches its most literal and most frightening form. You would never see it coming. A gamma-ray burst travels at the speed of light, which means the burst itself arrives at the same instant as any possible warning of it. There is no signal that could outrun it to tell us it was on the way. If a beam were aimed at Earth from a dying star 3,000 light-years away, the first we would know of it would be the burst itself reaching our atmosphere. The universe, in the gamma-ray burst, has built something very close to a perfect sniper, a weapon that can end a biosphere from across the cosmos, that fires without warning and against which there is no possible defense, because you cannot dodge or shield against a thing that arrives at the very speed of the information that would have warned you. There is a further twist that makes gamma-ray bursts almost unbearable to think about clearly, and it has to do with that narrowness of the beam. Because the energy is focused into two tight jets rather than spread evenly, a gamma-ray burst is, in a sense, a matter of aim. For any given burst, only the tiny sliver of the universe that happens to lie along the direction of the beam receives the full force of it. Everything else, everything off to the side, sees only a faint and harmless glow, if it sees anything at all. This means that for every gamma-ray burst we detect, pointed by chance in our direction, there are many others firing off in directions that never sweep across us, invisible to us precisely because they are not aimed our way. The sky is full of these beams, lancing out in every direction, and we only ever notice the ones that happen to point at Earth. It is a little like standing in a field at night while unseen searchlights swing across the darkness all around, and only registering their existence in the instant one of them sweeps directly across your eyes. Now, I want to be honest and calming here, because I do not want to leave you with a nightmare. The odds of a gamma-ray burst being aimed precisely at the Earth from close enough to harm us, within any span of time that matters to us, are very low. These are rare events, and the beams are narrow, and the galaxy is large. This is not a thing to fear in your daily life, but the universe does produce these bursts constantly. We detect, on average, about one gamma-ray burst every single day, each one coming from a random direction, from a dying star or a neutron star collision somewhere in the far reaches of space. Most of them are billions of light-years away, far too distant to affect us. But they are always happening. Every day, somewhere out there, a black hole is being born and announcing itself with a scream of gamma rays bright enough to briefly outshine the universe. And just to make the reach of these things concrete, let me tell you about a recent one. In October of the year 2022, astronomers detected a gamma-ray burst so powerful that they nicknamed it the brightest of all time. It came from a distance of about 2.5 billion light-years. 2.5 billion. And yet, even after crossing that almost meaningless expanse of space, even arriving from a source so far away that its light set out before complex life existed on Earth, it was still powerful enough to measurably disturb our planet's ionosphere, the upper layer of our atmosphere. From 2.5 billion light-years, it reached down and touched the air above us. Had that same burst occurred within our own galaxy and been aimed our way, it would not have gently disturbed the ionosphere. It would have been a global catastrophe. I want to pause on the sheer improbability of how we found these things, because it says something about the universe and about us. The Vela satellites were built for a completely human purpose, to police a treaty, to catch anyone secretly testing nuclear weapons. They were pointed at the Earth, watching for our own violence, and in the course of that grim and ordinary duty, they happened to catch flashes coming from the wrong direction, from far out in space, and in doing so they stumbled upon the most powerful explosions in the universe. There is something almost humbling in that. We were looking inward, at ourselves, worried about the destructive power we had learned to wield, and the universe quietly showed us that its own explosions dwarfed anything we could ever build by an amount beyond all comparison. Every nuclear weapon humanity has ever made detonated all at once would be nothing, less than nothing, beside a single gamma-ray burst. We went looking for the largest fires we knew how to light, and found that the dark was already full of infernos we had never dreamed of. And there is a subtlety about gamma-ray bursts that makes them even stranger to contemplate, which is that everyone we see is a message from the distant past. Because these bursts come from so far away, often billions of light-years, the light we detect today set out billions of years ago. The dying star that produced it is long gone, its black hole long since formed and settled. When astronomers catch a burst, they are not witnessing something happening now. They are receiving an announcement of an event that concluded before the Earth had formed, a birth cry of a black hole that has been silent for eons, only now reaching us. Every burst is a kind of time capsule, a flash of ancient violence arriving in our present. And that means the sky is not only full of these events, it is full of their echoes, a constant rain of old light from old catastrophes, arriving day after day from every direction, each one the final word of a star that died when the universe was young. So there is the thread tightened to its most extreme point. The rogue black hole was invisible, the magnetar was unpredictable. The gamma-ray burst is both, and worse, because it arrives at the speed of its own warning, from anywhere in the cosmos, in an instant, with lethal aim. It is the closest the universe comes to a bolt from the blue that no one could ever prepare for. And yet, for all its terror, a gamma-ray burst is still a single event, a single dying star, a single scream. It happens, and it fades, and the universe moves on. The next two entries on our list are not events at all. They are not things that happen and end. They are ongoing, silent motions, forces already acting on us as we speak, pulling our entire galaxy through space toward destinations we cannot see. And the strangest part is that with these final two, we stop being spectators watching distant violence, and we become the ones being moved. Part 9, Number 2, The Pull We Cannot See. For everything we have discussed tonight, you have been, in a sense, a spectator. You have looked out at dying stars and wandering black holes and screaming bursts of radiation, and even when the danger touched our atmosphere, you were still watching it from a safe remove, an observer of distant violence. But the second thing on our list is not something you watch. It is something that is happening to you right now as you listen. You and everyone you have ever known, and the Sun and the Earth and the entire Milky Way galaxy are being pulled through space towards something enormous, something we cannot see, something that has a grip on us so powerful that it overrides even the expansion of the universe. Astronomers call it the Great Attractor, and after decades of study we still cannot fully say what it is. Here is how we know it is there, even though we cannot see it clearly. In the 1970s, astronomers were carefully measuring the motions of galaxies, and they noticed something that did not fit. Galaxies are supposed to be drifting apart as the universe expands, carried along by the general stretching of space. But when astronomers looked closely, they found that our galaxy, and a great many others were not simply riding that expansion. They had an extra motion on top of it, a shared drift, all of them moving together toward one particular region of the sky. It was as though the expansion of the universe were the current of a great river, and yet here was a whole fleet of galaxies swimming against or across that current, all in the same direction, drawn by some unseen thing. The scale of this motion is difficult to hold in your mind. The Great Attractor is dragging the Milky Way, along with hundreds of thousands of other galaxies, toward a specific point in space at a speed of roughly 14 million miles per hour. Let me try to make that number physical for you. At 14 million miles per hour, you could travel from the Earth to the Moon in just over a minute. Our entire galaxy, everything in it, the Sun and its planets, every star you have ever seen, all of the hundreds of billions of stars in the Milky Way, is being carried through space at that speed, toward a destination about 150 million light-years away, in the direction of a region containing the great galaxy clusters of Hydra and Centaurus. And now comes the part that turns a curiosity into one of the most unsettling facts in astronomy. We cannot directly see what is pulling us. The Great Attractor lies in a region of the sky that astronomers, with a name that sounds almost mythological, call the zone of avoidance. This is the band of sky that is blocked from our view by our own galaxy. When we look in that direction, we are looking straight through the crowded, dusty, star-filled disk of the Milky Way itself, and the dust and gas and glare of our own galaxy obscure whatever lies beyond. So the thing that is pulling us, the enormous mass that has our entire galaxy in its grip, sits hidden behind a curtain made of our own home. We know it is there only because we can feel its pull. We are being drawn towards something we cannot see, its presence betrayed only by the motion it forces upon us. Astronomers have not simply given up, of course. Using infrared and radio telescopes which can pierce through some of the dust that blocks visible light, they have managed to peer partway into the zone of avoidance, and they have found large concentrations of galaxies there, great clusters of them, containing the mass of tens of thousands of galaxies like our own. But here is the puzzle that keeps the Great Attractor on this list. Even those enormous concentrations do not seem to be quite enough. The mass we can find does not fully account for the strength of the pull we feel, and so some astronomers suspect that behind the Great Attractor, farther out, there lies something even larger, a still more massive concentration of galaxies, sometimes associated with a structure called the Shapley supercluster, and that what we call the Great Attractor may be only a way station, the near edge of a flow that is carrying us towards something grander and more distant still. In the year 2014, astronomers mapped this flow of galaxies and gave our home supercluster a name, Laniakea, a Hawaiian word meaning immense heaven, and they showed that our galaxy sits within an immense basin of attraction, all of it draining toward these hidden masses. I want you to pause here and actually feel what this means, because it is easy to keep it as an abstract fact and miss the weight of it. Right now, as you lie there, as you breathe, you feel perfectly still. The ground beneath you feels solid and motionless. But you're not still. The Earth is spinning and orbiting the Sun, and the Sun is sweeping around the galaxy, and the entire galaxy is falling at 14 million miles per hour towards something no one has ever seen. You're being carried, at this very moment, toward a destination chosen for you by a mass hidden behind the curtain of the Milky Way, and there is nothing anyone can do about it. There is no steering. There is no slowing down. There is no changing course. Every living thing that has ever existed, every civilization, every creature, every one of us has been aboard this galaxy as it falls, and not one of us was ever at the wheel. We are passengers on something we cannot pilot, moving towards something we cannot see, and we did not even know we were in motion until we learned to measure it. And notice how gently this fear operates, because it is not really a fear of harm at all. Nothing about the Great Attractor is going to hurt you tonight, or in your lifetime, or in the lifetime of your civilization. The pull is enormous, but it is smooth and steady and slow, spread across timescales so long that from inside them we feel nothing whatsoever. If the Great Attractor were going to do anything dramatic to our galaxy, it would do it billions of years from now, long after the Sun itself has changed beyond recognition. So the fear here is not the fear of a threat. It is the quieter fear of realizing that you are not the author of your own trajectory, that a decision made by hidden masses long before you were born has set the entire galaxy on a path you cannot alter and did not choose. It is the fear of learning gently that you were never steering and that the thing steering is not even something you're allowed to see. That, I think, is the particular flavour of fear the Great Attractor offers, and it is different from all the ones that came before. The earlier entries threatened us with violence, with destruction, with things that could harm or kill. The Great Attractor does not threaten us with any of that. As far as we know, the journey toward it is not dangerous in any immediate sense. What it threatens is something more subtle and, in a way, more profound. It threatens our sense of agency, our sense of being in control of our own place in the universe. We like to imagine ourselves as at least the still centre of our own experience, the fixed point around which things happen. And the Great Attractor tells us gently but firmly that we are not even that. We are being moved. We have always been being moved, and the hand that moves us is hidden from our sight. Here is our thread, and see how far it has come. We started with the fear of things we would never see coming. The rogue black hole in the dark, the gamma ray burst arriving with its own warning. But the Great Attractor is not coming for us. It is not approaching. Instead, we are going to it. The motion has been reversed. The thing we cannot see is not hurtling toward us out of the dark. We are the ones being drawn, silently and continuously, toward it. And that reversal is the quiet turning point of this entire list. Because up to now, the danger has always been out there, something external that might reach us. Now the danger has become our own motion, our own helpless drift. The realization that we are already, right now, in the grip of something immense and invisible and beyond our power to resist. There is a way of picturing our situation that I find both dizzying and strangely beautiful, and it comes from that 2014 mapping I mentioned, the one that named our home Laniakea. What those astronomers did was trace the motions of thousands of galaxies and ask, for each one, which way it is flowing. And when they drew all those flow lines together, a shape emerged, like the watershed of a great river system seen from above. Just as every stream and creek in a terrain drains toward a shared basin, every galaxy in our region is drifting along currents that converge toward the same great gravitational hollow. They drew a boundary around all the galaxies whose flows lead inward toward our shared basin, and that boundary defines Laniakea, our supercluster, our true cosmic home address, containing our Milky Way and 100,000 other galaxies, all of us sliding down the same immense slope toward the Great Attractor and whatever lies beyond it. We are not just floating in space. We live on the side of a valley we cannot see, and everything around us is rolling slowly toward its bottom. And that image carries a quiet reversal of everything we usually assume about our place in things. We tend to think of ourselves as sitting still while the universe moves around us, as observers watching from a fixed vantage point. But the Great Attractor and the map of Laniakea tell us that stillness was always an illusion, born of the shortness of our lives. Nothing here is at rest. Our planet, our star, our galaxy, our entire supercluster of 100,000 galaxies, all of it is in motion, all of it flowing, drawn along currents set by masses we're only beginning to locate. You have never once been still, not for a single second of your life. You have been falling, along with everything you have ever known, toward a destination hidden behind the light of your own galaxy. And the only reason it feels like stillness is that you, and everyone around you, and the ground itself are all falling together, at the same speed, in the same direction, so that the motion becomes invisible from the inside. That, perhaps, is the quietest terror of all, the discovery that even your sense of standing still was never true, and yet, for all its strangeness, the Great Attractor is still something. It is a real mass, made of real galaxies, hidden but findable, sitting at a knowable distance within our own observable universe. We can point to where it is. We can partly see through the curtain. It obeys the ordinary rules of gravity and mass that we understand. It is mysterious only because it is hidden, not because it is impossible. But there is one more entry on our list, and the final thing, the thing at number 1, is not hidden within our universe. If it is real at all, it may lie beyond it. It may be a pull that comes from outside everything we can ever see, reaching in across the very edge of the observable universe, tugging on hundreds of galaxy clusters in a way that, according to our deepest laws, should not be possible at all. It is the most disputed, the most speculative, and, if it is true, by far the most profound fear on this entire list. Part 10, Number 1, The Tide from Beyond Everything. We have arrived at the top of the list, at the single most unsettling thing on it, and I want to prepare you for something before we begin. This last entry is different from all the others in one important way. Everything else we have talked about tonight is firmly established. The zombie stars, the wandering black holes, the magnetars, the quasars, the gamma-ray bursts, the Great Attractor, all of these are real, confirmed, measured parts of our universe. But the thing at number 1 is not settled science. It is disputed. Some astronomers believe it is real, and others believe it is not there at all. I am going to be completely honest with you about that uncertainty as we go, because the honesty is part of what makes it so haunting. Because if this one is real, it is not a threat to your body or your planet. It is a threat to the very foundations of what we think we know about the universe. It is called dark flow. The story begins in the year 2008, when an astrophysicist named Alexander Kashlinsky and his team were studying the motions of galaxy clusters, the enormous gatherings of hundreds or thousands of galaxies bound together by gravity. And they found something that, by every rule we hold dear, should not have been there. They found that hundreds of these galaxy clusters, spread across a huge swathe of the sky, were all moving in the same direction, at enormous speeds, as though they were all being pulled toward a single point far off in the distance. The clusters were streaming coherently together toward a region near the constellations of Centaurus and Hydra, at speeds of up to about 1,000 kilometers per second. Now, to understand why that is so disturbing, you have to understand one of the deepest assumptions in all of cosmology, an idea called the cosmological principle. It says that on the larger scales, the universe should be smooth and uniform, the same in every direction, with no special places and no preferred directions. Look far enough out, in any direction, and you should see basically the same thing. There should be no overall flow, no grand shared motion, because there should be nothing out there special enough to cause one. The cosmological principle is one of the foundations on which our entire picture of the cosmos is built, and dark flow, if it is real, violates it. Hundreds of galaxy clusters all streaming the same way is exactly the kind of thing the cosmological principle says should not happen. So what could cause it? What could pull hundreds of galaxy clusters, spanning billions of light years, all in the same direction? The mass would have to be immense, far greater than the Great Attractor, far greater than anything. And here is where it becomes truly strange. Kashlinsky's team suggested that whatever is doing the pulling might lie beyond the edge of the observable universe, beyond the edge of what we can ever, even in principle, see. I need to explain what that phrase means, because it is the key to the entire fear. There is a hard limit to how far we can see into the universe. The universe is about 13.8 billion years old, and light travels at a finite speed, so we can only see objects whose light has had time to reach us since the beginning. Because the universe has also been expanding, the actual edge of what we can observe sits about 46 billion light-years away in every direction, making an immense sphere, roughly 93 billion light-years across, that we call the observable universe. This sphere is not the whole universe. It is simply the part of it whose light has had time to reach us. Beyond that edge, there is almost certainly more universe, perhaps infinitely more, but it is forever hidden from us, because the light from it has not had, and may never have, time to arrive. That edge is not a wall, it is a horizon, a limit on knowledge, the boundary of everything we can ever observe. And dark flow suggests that something beyond that horizon, something outside the observable universe entirely, is reaching across it and pulling on the galaxy clusters inside. That is what makes it the number one fear on this list, because we are not supposed to be able to feel anything from beyond the observable universe. The horizon is meant to be a true limit. Nothing from outside it should be able to influence us. And yet, if dark flow is real, we are detecting the gravitational tug of a thing we can never see, a thing that lies outside the very edge of everything, exerting its pull on us from across the boundary of the knowable. Let me take you all the way out, one last time, further than we have gone all night. Rise up and away from the Earth, past the Sun, past the Milky Way, past the Great Attractor and the galaxy clusters streaming toward it. Keep rising until our entire observable universe, all 93 billion light-years of it, all its hundreds of billions of galaxies shrinking to a single glowing sphere adrift in a darkness we have no words for. That whole sphere, everything we can ever know, every star and world and living thing, is a single bubble of light. And now, watch. The bubble is drifting. It is being pulled gently and steadily towards something. But the thing that pulls it lies outside the bubble entirely, beyond its shining edge, in the dark we can never enter. Our whole universe, the sum total of everything we can observe, is being tugged toward a shore we will never reach and can never see. The interpretations of what that something might be are genuinely staggering. Some have suggested that dark flow could be evidence of other universes beyond our own, their gravity leaking faintly across the boundaries between cosmic bubbles. Others propose that it reveals that our universe is vastly larger than the part we can see, with enormous structures lying just beyond our horizon, exerting their pull on everything within. Both possibilities force us to confront the same vertiginous idea, that our entire observable universe, that sphere 93 billion light-years across containing every galaxy we have ever catalogued, might be nothing more than a small bubble within something incomprehensibly larger, and that the rules we have so carefully worked out, the physics we trust, might turn out to be merely the local bylaws of our tiny corner, not the laws of the whole. Now I promised you honesty, and here it is. Dark flow is contested. Since Kashlinsky first proposed it, other teams have gone looking, and the results have conflicted. Some studies, including analyses using more precise measurements of the ancient light left over from the Big Bang, have found no significant evidence for it at all, and have concluded that dark flow may simply be a statistical illusion, a pattern the mind and the mathematics found in noise. Other researchers maintain that the signal is there. The debate has not been settled. It is entirely possible that dark flow is not real, that the cosmological principle holds after all, and that there is no tide reaching in from beyond the edge of everything. I want you to hold both of those possibilities at once, because that suspension, that not knowing, is exactly where the deepest fear lives. Because here is what the top of this list has really been building toward, and it is the thought I want to leave you with as you drift. For most of this night, the terrifying things were objects, stars and black holes and bursts of radiation, things you could point to, things with a location and a size. But dark flow is not really about an object. It is about the possibility that our knowledge itself has an edge, that the confidence we feel about how the universe works might be the confidence of someone standing in a small, well-lit room, mistaking the walls of the room for the edges of the world. Remember the civilization at the centre of the Bhuta's void, careful and rigorous and permanently invisibly wrong. Dark flow raises the possibility that in some deeper sense we are all that civilization, that the universe we can see is a lit room inside a dark house, and that the laws we trust may be nothing more than the local rules of that one room. I want to be very clear that the doubt here is not a weakness in the story. It is the story. The scientists who question dark flow are doing exactly what science is supposed to do, refusing to accept an extraordinary claim without extraordinary evidence, checking and rechecking, insisting that a signal be real before we build a worldview on it. That is not timidity. It is the discipline that keeps us honest, the same discipline that lets us trust everything else on this list. And so, dark flow sits in a peculiar and fascinating place. It is right at the edge of what we can measure, at the very limit of our instruments and our methods, where a real signal and a statistical ghost look almost the same, and where honest, careful people can look at the same data and reach opposite conclusions. It may resolve in time one way or the other as our measurements sharpen, or it may remain for a long while exactly what it is now, a question mark placed at the outer boundary of the knowable. And whether or not dark flow itself turns out to be real, the possibility it opens will not go away, because that possibility is not really about one measurement. It is about the shape of our situation. We are creatures who can only know what light and information can bring us, and light and information have an edge, a horizon beyond which we cannot see, perhaps cannot ever see. Everything we have learned, every law we trust, every confident statement in every textbook was assembled from evidence gathered inside that horizon. And there is simply no way from the inside to be certain that what holds within our sphere holds beyond it. Dark flow is frightening not because it proves anything, but because it reminds us with unusual force that our knowledge has a boundary and that we cannot see past our own boundary to check whether the universe agrees with us out there. The most disquieting thing on this entire list is not an object at all. It is a limit, the edge of the lit room, and the humbling suspicion that we have been mistaking the walls of the room for the edges of the world. And so we come back, at the end to where we began, to the calm night sky. Go outside on a clear dark night and look up, and you will see the same thing humans have always seen. Steady points of light, quiet and patient and reassuring, wheeling slowly overhead. And I hope, after tonight, you will see it a little differently. Not with more fear, but with more honesty. Because that calm is real, but it is not the whole truth. Behind it are the stars that would not die, and the galaxy that eats, and the predators with no light, and the fire in our own sun, and the great nothing, and the magnetic monsters, and the brightest engines in creation, and the cosmic snipers, and the pull we cannot see, and perhaps, just perhaps, a tide reaching in from beyond everything. The calm you see when you look up is not a description of the universe. It is a report on the gentleness of your own eyes, which were built to see only the small, safe, nearby part. But I do not want to leave you frightened, because fear was never really the point. The point is wonder, the kind that only comes when the safe, simple picture falls away, and the true one, stranger and vaster and stranger still, rises up behind it. Every terrifying thing we have talked about tonight is also, if you turn it slightly, one of the most astonishing facts about being alive in this universe at all. We are small creatures on a small world, made of atoms forged in dead stars, aboard a galaxy falling through the dark towards something we cannot see, inside a bubble of light that may be adrift in an ocean we can never cross. And somehow, from inside all of that, we have learned to look up and to measure and to understand even the things that frighten us. The universe is far more terrifying than the calm sky suggests. It is also far more magnificent. And the same eyes that were built to see only the small, safe part have learned, against every odd, to reach out toward the rest. So rest now. Let the strangeness settle into wonder, and know that the quiet sky above you, whatever it hides, is still, tonight, watching over you as gently as it always has.